sorry for my English, it's not really good, but I do my best. I try to do my best. I'm from Argentina, and here we are presenting some preliminary ideas. There was much work to do here, but we think it's interesting to share some results. This presentation shows a couple of ideas to design corrugated surfaces, face gratings, with special cases of specular reflection. Typical diffusers are in fact corrugated surfaces, but in these presentations we will not concern on diffusion, but on specular reflections. It's something strange. We follow a proposal of ICA2019 Japanese to analyze and design a sub-wavelength reflectant surface. What kinds of reflections? The three examples we show something we call delayed reflection surfaces. The second example is multiple reflection surfaces, and the third reverberant tail reflection surfaces. At first, we will show some simulations of what is possible to get only in simulations in the actual state of our work. Then we will discuss how they can be designed. The simulations, first type, delayed reflection surface. Simulation shows a reflection of three different acoustic objects, each one with different delay in the top surface. Intentionally, it's not possible to see the surface in this initial state. We can see the delay that we can think there was a plane surface here. We show the same surfaces, same objects with different angle of incidence. Here it is possible to note that the reflection meets the border exactly. Delayed, but as if we were emitted by the top surface. Second type, multiple reflection surface. The simulation shows a surface producing different reflection patterns while reflecting a plane wave. This is the example. In the top was a treatment, first reflection, second reflection, third reflection, and a fourth reflection. Third type, reverberant tail surfaces. This simulation shows three surfaces, three different. The first on the left, there's a plane surface for comparison, and the other shows a reverberant tail with different delays. First, different delays and a reverberant tail, one surface. Well, here is a comparison with different wavelengths. The same surfaces, the same objects, different wavelengths of plane wave. What variables are involved in the design of these surfaces? We took as a basic work this paper of ICA2019 to start analyzing corrugated surfaces as analogous to a linear array. Different slit depths are equivalent to different phases in the array. Then he used known concept of phase array theory to analyze these surfaces. Here, the example of what he proposed. He proposed considering each slit as a source of the linear array. The reflection angle of the surface is equivalent to the radiating angle of the array. In this way, here is the expressions he get to design the surfaces. Points labeled with A prime and A are in phase if B is ahead of A by a value of delta phi, And then this, for a given wavelength, the relationship between the parameters is expressed by theta is the reflection angle, or the emitting angle in the case of the array, and it is obtained as arcsine of lambda over 2p, and it is that in a continuous case that we can consider will be the phase gradient of the array. Selecting appropriating phase change delta phi of the array, it is possible to obtain the desired theta. It is important to notice that theta can be dependent of x, generating a complex reflection pattern of a plane wave. The aim of Su's work was to determine conditions to get dispersionless reflection with theta independent of wavelengths, and he thinks that here there are lambda is in the argument of the arcsine. Su states that it is necessary to delta phi to be proportional to the wave number to be dispersionless. And he concludes that every array with delta phi proportional to wave numbers generates dispersionless reflections. For last, Su shows that all delta phis produced by any corrugated surface must be proportional to wave number, and then it is dispersionless. Given a group of delta H of a slit, the phase change delta phi is related to the delay for the wave to travel along the slit, and this is the expression where it can be seen that is proportional of the wave number and cancel this term in theta. In summary, a gradient surface produces phase changes that are necessarily proportional to K, to wave number, and then obtain the final expression where delta H over delta X is equivalent to the gradient of the profile of the section. In this case, it's a line, but it may be a function of X. Such term in a continuous case we can imagine must be consider the profile gradient. Consider this continuous case, given the same theta reflection angle, the section of the corrugated surface can be obtained by this equation. This is the design equation. If you know the emitting angle decided as a function of x, obtaining this integral can derive the section of the profile, where the constant integration, Su in his work mentioned the constant integration that must be selected to ensure that Hx, the profile, must not be always be positive for logical point of view. But H0 can be selected as a design parameter to set a convening delay as shown in the simulation. The first example show at the beginning simulated surfaces with the same gradient profile but different H0. Here's the profiles. And in this case, it's evident that the reflection delay comes from the borders of surfaces. The second example shows, shown at first slides, exhibit different reflection patterns. It was possible taking the idea of Su of considering the slits as an array and intersected interspreading two arrays, and here in black and red This, of course, spreading out the surfaces limit the bandwidth, but other parameters we can consider, for example, the width of the slits to ensure that this not ruins the intention of the design. Here, the second simulation with intercalated slits with different design parameters. This was the complex reflection pattern shown at first. But why more than two reflection patterns are presented here? Well, this is because interference between open ends of adjacent slits. One adjacent slit can be considered as an open-ended tube. This generates an inverted pressure reflection on the open end, as is well known. But if a tube array is considered, the open-ended reflection does not occur because the other tubes modify impedance. Here are no reflections. This is simulation of an array of tubes. This, in fact, was the principle we used to design the third example. In this case, we take advantage of the interaction between adjacent slits to produce a reverberant tail. As we show here, the delay was made by the constant integration, different depth, mean depth, and the reverberant tail because we intercalate two different lengths. Here's a comparison with different wavelengths of the same surface with a reverberant tail. This may seem more, the time is the same, because of different wavelengths, there are more cycles of the reflections. Well, summarizing that, phase gratings are commonly used in diffusers, but it may be of interest to consider their use in other situations. These were 4 points. Constant reflection angle with delay was one of the possibilities. Non-constant reflection angle with or without delay but remaining dispersionless behavior, combined reflections of interspread profiles, and profiles exhibiting a reverberant tail. This is only a brief description of simple ideas related to corrugated surface. And that's all. Thanks.